Hey guys, so this is the second part for week 10, and I'll be going over the second quiz you took, which was the energy quiz. Okay, I have a drawing of what was given on the quiz up here, and I'm also going to put the question in the description, so just go ahead and read the question before looking at this. Okay, so here we are. We have a mass which is going to fall down this left side, and let me trace the trajectory that's described. It goes down, it goes past this rough part, and goes to the smooth part, comes up, comes back down, goes through the rough part a second time, and stops at point B. Okay. And so, the law or definition I'm going to use here is going to be the conservation of energy, because the only thing that is changing here is the change in gravitational potential energy, and there's some work being done by friction. Okay, so let's write out the conservation of energy when we have non-conservative forces doing work. That is that the kinetic energy at the initial point plus the potential energy at the initial point. Let me go ahead and fix this real quick. Should have a little more on that side. Okay. Plus the work done by non-conservative forces, that's what the NC means. Now we have to be careful because this is going to be along the entire trajectory. Just to be clear. Trajectory. From R1 to R2. Okay. We'll see what that means in a second. That's equal to the kinetic energy at a point R2 plus the potential energy at a point R2. Alright. So let's see what's going on. Well, in this first two part, or in the smooth part, the only force acting on it is gravity and normal force. Okay. And normal force doesn't do any work and doesn't really change energy, it just constrains it to move along a certain path. So the only free body diagram I'm really interested in is the free body diagrams whenever it is moving in this rough patch. And we will see it will depend on which way it's moving. So in the first half of the trajectory, it's moving from left to right. In the second half, it's moving from right to left. So when we're moving right, the free body diagram looks like this. We have normal force, gravity, and we're going to have friction with its full value mu(n). Okay. And just from summing the forces in the y direction, that must be 0. This will tell us that n is equal to mg. Alright. So we know that, and that's in the y direction. Alright, so that's using this coordinate system, which I haven't introduced yet. But if I hadn't introduced it, if I sum the forces in the vertical direction here, the particle isn't moving along the rough patch in the y direction. Right, or in this vertical direction. So we would have n is equal to mg, and then moving left on the second part of the trajectory, when it moves down this ramp but then through this rough patch, so in rough patch for both of these. Then we have the normal force and mg once again, making the normal force mg. But now mu(n) is to the right, since it's moving to the left. Okay. So this would be all the law or definitions we need. Maybe one more thing is that the potential function for a conservative force is equal to the negative, well, rather, let's write it like this. Conservative force's x component is equal to the negative derivative of u with respect to x. In general, it has to be a partial derivative. But here, we're going to see this friction force, this gravity, for example, only acts in one direction. Okay, so if we have the y component being the component of the force, where all the force is for gravity, for example, then the derivative of the potential function with respect to y times -1 should give us the force. Okay. So we need a coordinate system, and the one I chose was starting at the rough patch. Okay, I put the origin on the left side, where at first it's the rough patch, on the ground, and I chose positive x to the right and positive y up. So let's go ahead and find what each of these things are in conservation of energy in this coordinate system. Now, R1 and R2 need to be well defined. So R1 is going to be, well, let's just write it as a point. Okay, so let's not write equals. R1 is going to point to the point 0h, which is where it starts. So this is 0h here, right? Okay, let's go ahead and indicate that. 0h. And we are ending at this point here, which is B0. So that's how I'm going to use this unknown point B in my coordinate system where the object starts. Okay, I'm going to label it as B from the origin, right? And y is equal to 0 here. So we're going from R1 to R2, B0. Right? So the kinetic energy at R1, well, it starts at rest. So K at R1 is 0. Now, at B0, that's where it stops after traveling with total trajectory. The kinetic energy there is also going to be 0. So I'm just going to sort of cheat a little bit. Instead of writing K at R2 is 0, I'm just going to write, well, 0 is also equal to K at R2. So it's just a little cheat there. There's no significance to me writing it this way. So that's this term taken care of, and this term taken care of. Now we need to take care of the other ones. Well, let's do the potential, since it looks to be the least complicated. This one looks to be the most complicated. So, outside of the rough patch, right, we just have gravity and normal force here. So we can write a potential function for the gravitational force. And I'm going to guess it to be, in our coordinate system, u of gravity, u as a function of y, is going to be mgy. And now let's check it. We take the negative derivative of u with respect to y, and we get minus mg. And in this coordinate system, that should be always the potential function for gravity. Okay. So, because gravity is always pointing mg down in the negative y direction. So this potential function will work. It's independent of velocity, what side of the track we're on, whether we're in the rough part or the smooth part. Okay. And so there are no other forces that are conservative of this problem that do work. So, u at R1, we found, which is going to be u at 0h, well, we take mg times the y coordinate, so mgh. Right? U at R2 is mg times the y coordinate at R2. Well, the y coordinate is 0, so it should be 0. So we have a gravitational potential energy of mgh here, and a gravitational potential energy of mg times 0 at the bottom at point B. Okay? So now we have all the terms except for this work done by non-conservative forces along the entire trajectory from R1 to R2. Okay? So, as we've shown, friction is the only non-conservative force doing work on this object. Alright? And when we move to the right in this rough patch from 0 to L, so this is x equal to 0 here, this is x equal to b here, and this is x equal to L here. Alright? When it's moving right from 0 to L, friction's to the left. And then it goes up here, there's no friction, it comes back down, and then it goes from L to B where it stops, where the friction force is then going to be to the right. Okay? So let me go ahead and get this annoying little play bar out. Okay. So the work done by, it's helpful to look at the picture, so make sure you have a picture drawn of this while you're doing this. The work done by friction, the non-conservative force from R1 to R2, along the entire trajectory, well, we split it into two parts. So we do the work done by friction, all right, from 0 to L, and then from L to B. So we go from 0 to L first, where the friction force is to the left and N is mg. And then we go from L to B, and now the friction force is to the right. So we write a positive mu mg. These integrals are easy because it's a constant. We're integrating a constant with respect to x, so we just get minus mu mg L minus 0, so we just get mu mg L, and then plus mu mg B minus L. Verify that that is indeed the integral here. Okay. Now what we do is we plug everything into this equation here. So let's take this equation here and plug in everything we know. We've calculated everything. Okay. So, whoa, that is not what I meant to do at all. Let's try this one more time. Copy, paste. Okay. So K at R1. Well, remember, starts at rest, that's 0. And then we got plus U at R1 is mgh, plus the work done by non-conservative forces. We just calculated the work done by friction along the entire trajectory. So it's minus mu mgl plus mu mg B minus L. Alright, that's equal to K at R2, 0, it ends at rest, plus U at R2, 0. Final gravitational potential energy, 0. Now we just solve for B. Okay? So there, you just solve it however you want. The best way to go about it is I would divide both sides by mu mg. Sorry, this is already running a little bit long, so I'm going to wrap it up here. And so if I divide both sides by mu mg, this term becomes h over mu, this term becomes negative L, and this current term becomes B minus L. So we get h over mu minus L, and then plus B minus L is equal to 0. And then we solve for B, and we get B is equal to 2 times L minus h over mu. Okay. And that's my point B in this coordinate system where I have it defined, right? So you have to always look at your coordinate system. That's it. All right. All right. So thank you, and I'll see you guys next week in recitation.